Hello students, welcome to physics class. Today we discuss pressure exerted by a liquid column. Suppose we are taking a liquid in a vessel of height h and cross-sectional area a. Let's say the density of the liquid is rho. So this liquid will exert a pressure on the surface of this container. Let's find what is the pressure exerted by the liquid column on this walls of this container. So weight of the liquid column is equal to, we can calculate what is the weight of this liquid column, which is actually the thrust on this surface. So the weight of the liquid column is equal to W is equal to mass of the liquid into G, acceleration due to gravity. So the weight of this liquid column is equal to volume into density. That's mass of the liquid is equal to volume into density into acceleration due to gravity. That is the weight. So the volume is equal to area cross section into H. That's the volume of this vessel or volume of this liquid. That's A into H. Density is given as rho into acceleration due to gravity G. A H rho G. That's the weight of this liquid column which is acting on this plane surface of area A. So we can consider that's a normal force. So that's a thrust acting on it. So we are writing as the thrust is equal to A H rho G. Thrust is nothing but the force which is acting normal to any surface is known as thrust. So the pressure is equal to thrust by area. That is, thrust is equal to A H rho G divided by area A. That is, pressure is equal to H rho G. You see that the pressure exerted by this liquid column of height h is equal to P is equal to h into rho into G. G is constant. And see, the pressure exerted by a liquid column is directly proportional to height of this liquid column and density of this liquid column. Actually, the pressure exerted by any liquid column is directly proportional to the height of this liquid column and the density of the liquid taken. That are the factors affecting the pressure exerted by a liquid column. Now see, pressure at a particular depth is a constant because you know it is directly proportional to h. When height changes, pressure also changes. If you are taking the 2 points in this liquid column A and B, we can say that the pressure at A and pressure at B are not equal. They are different. We can say as the height to point B is greater than the height to the point A. So we can say pressure at B should be greater than pressure at A. So now let us discuss what is the effect of gravity on fluid pressure. What is the effect of gravity on fluid pressure? For that, here we have a liquid of density rho which is taken in a vessel. And in this liquid, the liquid is at rest. So in this liquid, we are taking a very small cylindrical liquid element. A very small cylindrical liquid element of area cross section. Say area cross section of this cylindrical element is A. So in the horizontal direction, as the liquid is at rest, the total force should be 0. Actually, on the cylinder, in the horizontal direction, the pressure is acting. But in the horizontal direction, as the liquid is at rest, this element is not in motion. So there is no horizontal force acting on the total horizontal force acting on this liquid element, cylindrical element is 0. Here a pressure P1 is acting on this face in the downward directions and a pressure P2 is acting in this face. Now let us calculate what is the force due to this pressure. The force due to the liquid pressure at the top, that is in this phase 1. The force due to the liquid pressure at the top of the cylinder can be written as F1 is equal to P1 into A. F1 is equal to P1 into A, which is acting vertically downward. That is in downward direction. The force due to liquid pressure at the bottom here, P2 P2. A pressure P2 is acting on this bottom. So we can write as the force is equal to P2 into A. That is, it is acting in the upward direction. That force is acting in upward direction. So one more force is there. That is the weight of this cylinder. The weight of the cylindrical liquid element. That's equal to weight of the liquid cylinder acting downward is equal to W is equal to M into G. What M is the mass of this cylindrical element and G is the acceleration due to gravity. So we can write as volume into density into G. Mass can be write as volume into density into G. That's become weight. So the volume is equal to, let's say, H is the height of that cylindrical element into area cross section. So A into H is the volume into rho, volume into density become mass of this cylindrical element into G become weight of the cylindrical element. So you know that weight is always acting vertically downward. But as the liquid cylinder is in equilibrium, as the cylindrical element of this liquid is at equilibrium, the net force in the downward direction should be equal to the net force in the upward direction because there is no motion for this cylindrical liquid element. So net downward force is equal to net upward force. So what are the downward forces? One is the F1 which is acting vertically downward. And another one is the weight of this cylindrical element which is acting vertically downward. So the net downward forces are F1 and W. So F1 plus W. Both are in downward direction. And we have an upward force that is in the bottom face, that is F2 in the upward direction. So the net upward force is F2. So equate them because the cylindrical element is at equilibrium. The net force is equal to 0. So rearrange this equation, that is F2 minus F1. We are taking this F1 to right side. F2 minus F1 is equal to W. Or what is F2? F2 is equal to P2 into A. And F1 is equal to P1 into A. P2A minus P1A is equal to weight. Weight is equal to A H rho G. That is weight. So A is common in all terms. So we are get cancelled. So P2 minus P1 is equal to H rho G. P2 minus P1 is equal to H rho G. That is the P1 is the pressure acting on this face and the P2 is the pressure on this face. See the pressure difference between them. P2 minus P1 is equal to H rho G. That is the pressure difference between these 2 points in this liquid. It shows that when the height is different, the height from the water level is different, the pressure is also changed. That is, there is a pressure difference between these 2 points. P2 minus P1 is equal to H rho G. Suppose if you shift the point 1, that is this face, into the surface of this liquid. If you shift the point 1 to the liquid surface, so suppose this face of the cylinder is here, then we can write the P1 is equal to the atmospheric pressure because the pressure acting at this point is only the atmospheric pressure because above that there is no liquid, only atmosphere. So that is atmospheric pressure. So we can write P1 is equal to atmospheric pressure. And we can simply write as, instead of P2, we can write as P. Say the P is the pressure on the bottom face. Now see, we can rewrite this equation as, instead of P2 we are writing P, instead of P1 we are writing as atmospheric pressure. So we will write this equation as, take this P1 to right side, so it becomes PA. P is equal to PA plus H rho G. What is PA? PA is the atmospheric pressure. If you are taking this point is on the surface of the liquid, no other liquid pressure, only the atmospheric pressure is there. So we are writing P1 is equal to PA. And P2, no need to write as P2, is simply writing as P. So P is equal to PA plus H rho G. So the difference between the pressure at this top and at any point inside the liquid can be write as P minus PA. P minus PA is equal to H rho G. That is, if you want to find what is the pressure at a depth H from the liquid surface, it's equal to atmospheric pressure plus H rho G. And the difference between, that's P and PA. P minus PA is equal to H rho G is known as gauge pressure. That is P minus PA, the excess pressure. P minus PA is equal to H rho G is known as gauge pressure. The gauge pressure at a particular depth H is equal to H rho G. So that's the effect of gravity on the liquid pressure. Now let us see what is atmospheric pressure and how can we measure the atmospheric pressure. The atmospheric pressure is the pressure exerted by the atmosphere. It is known as atmospheric pressure. So it is measuring like this way. If you are calculating what is the force exerted by an air column on a unit area of Earth's surface is equal to atmospheric pressure. If you are imagining a column of air of unit cross-sectional area, which is starting from the surface of the Earth and extended up to the end of the atmosphere. Imagine an air column of unit cross-sectional area starting from the surface of the Earth and till the end of the atmosphere. So that air column is filled with air actually. So it will apply a force on that area. So that force is known as atmospheric pressure. That is the force exerted by an air column of unit area of Earth's surface is equal to atmospheric pressure. And atmospheric pressure is calculated approximately in the sea level. The normal atmospheric pressure is 1.013 into 10 raised to 5 Newton per meter square or Pascal. So the atmospheric pressure can be measured by using a simple device known as Mercury Barometer. It is designed by a scientist named Torricelli. So it is also known as Torricelli's barometer. So a Torricelli's barometer or a Mercury barometer consists of 1 meter long tube, open at one end and the other end is closed. And it is completely filled with mercury. Suppose that long tube is completely filled with mercury. And close the open end with a thumb and inverted it to a trough of mercury. Inverted to a trough containing mercury. So you can observe that the mercury level falls and it be stable at a height of 76 centimeter. At a height of 76 centimeter from the mercury level. Always it is observed that the mercury, once you are inverting the tube to a mercury trough, it is observed that the mercury falls and be constant at a particular height of 76 centimeter above the mercury level in the trough. So here, as it is inverted by closing the open end, here we have no air, or we can be considered it is a vacuum, and it is known as Torricelli's vacuum. The pressure at this area is equal to 0. So if you are taking this point as A, and the pressure in this region is equal to 0. Now consider two other points B and C, which is in the same level. B and C in the same level. C is the top point of this mercury level, the high. Okay. So the pressure acting at the point C is atmospheric pressure. But we know that from Pascal's law, as C and B are the points in the same level, pressure at C should be equal to pressure at B. So we are writing pressure at B is equal to pressure at C. But we know that pressure at point at point C is nothing but atmospheric pressure. The pressure at the point C, as this point C lies at the top point of the surface of this mercury, no other pressure is acting on it, only the atmospheric pressure. So pressure at point C is atmospheric pressure, but C and B are the point on the same level of liquid. So pressure at C should be equal to pressure at B. So we are writing PB is equal to PC is equal to atmospheric pressure. Now if H is the height of the mercury column and rho is the density of mercury, you know that mercury column having a height of 76 centimeter, and say rho is the density of mercury. So what is pressure at point B? Pressure at point B can be write as the pressure at point A plus H rho G, because this can be considered as a mercury column of height H. So the pressure of this column is equal to H rho G, H rho G into plus pressure at point A. Pressure at point A is 0 plus H rho G. So PB is equal to PA. You already see PB is equal to PA. So atmospheric pressure is equal to 0 plus H rho G, or atmospheric pressure is equal to H rho G. Substitute this value. H is equal to 76 centimeter. 76 centimeter we are writing in meter as 0.76 meter into rho, density of mercury 13.6 into 10 raised to 3 into acceleration due to gravity 9.8. So we are getting approximately 1.013 into 10 raised to 5 Pascal. The atmospheric pressure is calculated by using this Mercury Barometer or Torricelli Barometer as 1.013 into 10 raised to 5 Pascal. Now let us see another device for the measurement of pressure. So open tube manometer. Open tube manometer is a device used to measure the pressure of a gas enclosed in a vessel. Suppose here we have a vessel. We want to measure what is the pressure inside this vessel. What is the pressure inside this vessel? So we can use an open tube manometer. This is nothing but a U-shaped glass tube. It's a U-shaped glass tube open to the atmosphere. One end is open to the atmosphere and the other end is usually connected to the vessel where we want to measure the pressure. And usually this tube, glass tube, is filled with some liquid. Say it is filled with a liquid of density rho. It is filled with a liquid of density rho. So at this point A, the pressure acting is the pressure exerted by this vessel, or the point A, we have a pressure, that is the pressure inside this vessel. That is, we can write as P is equal to PA. A and B are the 2 points on the same level of a liquid at rest. So we can write pressure at A is equal to pressure at B. So we are supposed to measure pressure P. What is the pressure inside this vessel? So we can write as it is equal to pressure at B. How can we calculate the pressure at B? Pressure at B is equal to, we are writing as P, which is equal to the pressure inside the vessel. That is P is equal to pressure at point C plus H rho G. What is H? H is the height difference between the point B and C. Rho G, H rho G. But if this end is open to the atmosphere, we can write the pressure at C. Pressure at C is equal to atmospheric pressure. That's equal to P is equal to PA plus H rho G. P is equal to PA plus H rho G. In this way, we can measure what is the pressure inside this vessel. So that is a open tube manometer. By using an open tube manometer, we can measure what is the pressure inside a vessel. And by using a Mercury Barometer or Torricelli's Barometer, we can measure the atmospheric pressure. That's all today. Thank you.